Find somewhere comfortable. You don't need to sit up straight or hold anything in your mind. You don't need to follow this closely or remember a single word of it. Just let the words come to you the way warmth comes through a window, without effort, without asking for it. We're in no hurry tonight. If today was hard, you can set it down now. Whatever you've been carrying, the decisions, the small anxieties, the things you said or didn't say, none of that needs to come with you into this hour. Tonight, we're going to talk about light, not in a way that requires anything from you, just gently, the way you might turn a beautiful object over in your hands before sleep, noticing its weight, its strangeness, the way it catches what little light remains in the room. Because light, it turns out, is one of the most quietly astonishing things in the universe. And the question of what it actually is, what it's made of, how it moves, what it does when no one is watching, that question has occupied some of the greatest minds who ever lived. It has started arguments that lasted centuries. It has kept people awake in candlelit rooms, scribbling calculations they couldn't quite make work. And the answer, when it finally came, was stranger than anyone had imagined. So settle in. Let your body grow heavy. Let your breathing slow to whatever pace feels natural. The words will arrive on their own. Some of them you'll catch, and some of them will drift past, and both of those things are exactly right. We begin a long time ago with two men who disagreed. In the second half of the 17th century, there was perhaps no scientific mind more celebrated in the world than Isaac Newton's. He had described the motion of planets. He had invented a new form of mathematics. He had, in a very real sense, rewritten what it meant to understand the physical world. And when Newton turned his attention to light, to the pale beam that entered his darkened room through a small hole in a curtain and spread into a rainbow on the far wall, he formed a view that would shape physics for more than 100 years. Newton believed that light was made of particles, tiny, fast-moving corpuscles, he called them, projectiles fired from a source and traveling in straight lines until they struck something. The idea felt solid, intuitive. You could picture it. Light behaved in so many ways, like something thrown. It cast sharp shadows. It bounced off mirrors at neat, predictable angles. It traveled in straight lines the way a stone thrown in a vacuum would travel. Newton's corpuscular theory, as it came to be known, had the satisfying quality of fitting the world as people experienced it. Across the Channel, in the Netherlands, a quieter and in some ways more imaginative physicist named Christian Huygens was thinking about light rather differently. Huygens was a brilliant man. He had discovered Saturn's largest moon, had built some of the finest telescopes of his age, and had a gift for mathematical elegance. And Huygens thought Newton was wrong. Not wrong about everything, not even wrong in a way that was easy to prove, but wrong about light being particles. Huygens proposed, instead, that light was a wave, not a wave in water or air exactly, but a disturbance propagating outward through some medium, spreading in all directions from its source, the way a ripple spreads from a stone dropped into still water. His model could explain reflection and refraction, the bending of light as it passes from air into glass, in a different way from Newton's, and in some respects more cleanly. He published his wave theory in 690 in a careful and beautifully reasoned treatise. And then almost nobody listened. This was not because Huygens's arguments were weak. It was, in large part, because Newton was Newton. His authority in natural philosophy was so immense, so deeply woven into the intellectual fabric of the age, that to contradict him was something close to heresy. Newton had not merely been right about many things, he had been right about the fundamental machinery of the cosmos. Who was anyone to say he had got light wrong? And so Huygens's wave theory sat, largely unread and largely unchallenged, while Newton's corpuscular picture held the field. This is one of the quieter ironies of scientific history. Not that a great mind was wrong. That happens often enough. But that his wrongness was preserved by the very greatness of everything else he had done right. Authority. Even the authority of genius can become a kind of weight that presses down on the truth. For over a century, the corpuscular theory dominated. And then, in 1801, a young English physician and polymath named Thomas Young performed an experiment in a darkened room, and everything began to shift. Young was a remarkable person. He could read by the age of 2, spoke a dozen languages as an adult, and had made contributions to the deciphering of the Rosetta Stone alongside his work in optics. He was also, by all accounts, the kind of mind that simply could not leave a good question alone. And the question of what light was had been nagging at him for some time. His experiment was deceptively simple. He took a light source and placed in front of it a barrier with 2 narrow slits cut into it, side by side, very close together. Behind the barrier he placed a screen. If Newton was right, if light was particles, the answer should have been obvious. 2 bright bands on the screen, one behind each slit, like the shadows of 2 windows. Particles go through one slit or the other and land behind it. Clean, direct, predictable. But that is not what Young saw. Instead, on the screen behind the barrier, there appeared a series of alternating bands, bright, then dark, then bright, then dark, spreading out in a regular pattern. Not 2 bands. And the dark bands were the strangest thing of all. They appeared in places where, if both slits were open, you might expect more light, not less. Young recognized immediately what this meant. It was interference. The same phenomenon you see when 2 sets of ripples on a pond meet each other, where the crests of one wave arrive at the same moment as the crests of another. They reinforce each other, and you get a higher wave. Where the crest of one arrives at the same time as the trough of another, they cancel each other out. That pattern of reinforcement and cancellation, bright where the waves add together, dark where they subtract, is the signature of wave behavior. Particles simply cannot do it. Light, Young concluded, was a wave. Huygens had been right. The response from the scientific establishment was, initially, almost contemptuous. A critic, writing in the Edinburgh Review, dismissed Young's work as destitute of every species of merit. The paper in which Young described his experiment was largely ignored for years, partly because it contradicted Newton, and partly because Young's writing style was, by his own later admission, not always the most accessible. It would take decades and the independent work of the French physicist Augustin-Jean Fresnel to bring wave optics fully into the mainstream. By the 1820s, the mathematical framework for describing light as a wave was becoming too powerful to dismiss. The interference fringes in Young's experiment were real. The wave theory was real. Newton, on this particular question, had been wrong. But the story does not end there. Because as the wave theory of light settled into its new authority, comfortable and seemingly complete, a new set of puzzles was quietly gathering at the edges. Puzzles that the wave picture, for all its elegance, could not explain. The argument was not over. It had only moved into a stranger and more interesting place. For a moment, let the wave picture of light simply be. Let it unfold slowly. The way a long and patient explanation can sometimes feel like a kind of rest. By the middle of the 19th century, a Scottish physicist named James Clerk Maxwell had done something extraordinary. He had written down a set of equations, 4 of them, that described the behavior of electric and magnetic fields with a precision and completeness that felt almost architectural, as though the universe had been waiting for someone to draw its blueprint. What Maxwell's equations revealed when you followed them to their conclusion was something that nobody had quite anticipated. A changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. The 2 fields sustain each other, each one calling the other into being as they move through space together. And when Maxwell calculated the speed at which this self-sustaining disturbance would propagate, He found a number that matched, with astonishing precision, the measured speed of light. The conclusion was almost inescapable. Light is an electromagnetic wave. Not a wave in water, not a wave in air, not a wave in any material substance at all. A wave in the electromagnetic field itself. Oscillating electric and magnetic fields, oriented at right angles to each other and to the direction of travel, rippling outward through empty space at roughly 300 million meters per second. This is worth sitting with for a moment. When light crosses the room to reach your closed eyelids, what is crossing that room is not a thing you could hold or weigh. It is a pattern of disturbance, electric and magnetic fields fluctuating in a rhythm so rapid that the human mind can barely form a picture of it. And yet that pattern carries energy. It carries information. It carries, in some deep sense, a description of everything it has passed through on its way to you. Every light wave has two fundamental properties, wavelength and frequency. Wavelength is the distance between one crest of the wave and the next, the length of a single cycle of oscillation measured in space. Frequency is how many of those cycles pass a given point each second, measured in cycles per second, which physicists call hertz. These two quantities are not independent. Because all electromagnetic waves travel at the same speed in a vacuum, a longer wavelength means a lower frequency, and a shorter wavelength means a higher frequency. They are inversely linked, the way the length of a musical note and the number of notes you can fit into a second are linked. Visible light, the narrow range of electromagnetic waves that the human eye can detect, spans wavelengths from roughly 380 to 700 nanometers. A nanometer is 1/1000th of a meter, a distance so small that millions of them fit within the width of a human hair. At the long end of that visible range, around 700 nanometers, you have red light. Move toward shorter wavelengths and you pass through orange, yellow, green, blue, and arrive at violet around 380 nanometers. The colors of the rainbow, which Newton himself catalogues so carefully, are simply electromagnetic waves of different wavelengths, different frequencies, different energies, and the human eye has evolved to distinguish them. But visible light is only a tiny fraction of the full electromagnetic spectrum. Extend the wavelength further beyond red, and you enter infrared, the warmth you feel from a fire without seeing it. Further still, and you reach microwaves, and then radio waves which can have wavelengths of meters or even kilometers. In the other direction, beyond violet, lies ultraviolet, the frequencies that cause sunburn. Beyond that, X-rays, which can pass through soft tissue but are absorbed by bone. And, at the highest frequencies of all, with wavelengths smaller than an atom, gamma rays, released in the hearts of stars and in the decay of radioactive materials. All of these, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, are the same phenomenon, oscillating electric and magnetic fields propagating through space. The same equations describe them all. The only difference is frequency. Now, think again of that stone dropped into still water. Watch the ripples spread outward in concentric circles. Each ripple is a crest of the wave, and between each pair of crests is a trough. The distance between crests is the wavelength. The speed at which the crests travel outward is the wave speed, and if two stones are dropped close together, two sets of ripples spread outward, and where they meet, something interesting happens. Where a crest from one set of ripples meets a crest from the other, the water rises higher. The two waves reinforce each other. This is called constructive interference. Where a crest from one set meets a trough from the other, they cancel and the water is briefly still. This is destructive interference. The result, in the region where the two sets of ripples overlap, is a complex and beautiful pattern of high water and still water, arranged in irregular geometry. This is exactly what Thomas Young saw on his screen. Two slits, two sources of light waves spreading outward, and where those waves overlapped, the same pattern of reinforcement and cancellation. The alternating bands of brightness and shadow that had so puzzled Newton's defenders was simply the water ripple pattern translated into light. By the late 19th century, the wave picture of light felt genuinely complete. Maxwell's equations described not just how light traveled, but how it interacted with matter, how it was generated by moving charges, how it was absorbed. The spectrum had been mapped. Interference and diffraction, the spreading of waves around corners and through gaps, had been measured and predicted with extraordinary accuracy. Light was a wave, a beautiful, mathematically precise, deeply understood wave. And then something strange appeared at the edges of the picture. Not a dramatic crisis, not an obvious contradiction, just a small, persistent puzzle about how hot objects glow, a puzzle that, when followed patiently to its conclusion, would quietly dismantle everything. Every object that has warmth emits light, not always light you can see. At room temperature, the light an object emits is infrared, below the threshold of human vision. But heat something further, and it begins to glow, red, then orange, then yellow-white, then a brilliant blue-white at the highest temperatures. The color of a star tells you its surface temperature. The color of iron in a forge tells you how hot the fire has been. This relationship between temperature and the color of emitted light was well known by the late 19th century, and physicists had been trying to explain it mathematically for decades. The object they used as a theoretical model was called a blackbody, an ideal surface that absorbs all the light that falls on it and emits light purely as a function of its temperature, without any complication from the material's own particular chemistry. Real objects are more complex, but the blackbody was a useful simplification, and laboratories could build reasonable approximations of one using a small cavity with a tiny hole, like a hollow sphere with a pinhole opening. When physicists measured the spectrum of light coming from a blackbody, the distribution of energy across different frequencies, they found a characteristic shape. At low frequencies, the energy was low. It rose to a peak at some intermediate frequency that depended on temperature, and then fell away again at higher frequencies. The peak shifted toward higher frequencies as the temperature increased, which is why a hotter object glows bluer. The problem was that classical wave physics could not reproduce this curve. When physicists applied the wave theory of light to the blackbody problem, the mathematics predicted something deeply wrong. At high frequencies, the predicted energy should keep rising without limit, not fall away. A blackbody, according to the classical theory, should radiate an infinite amount of energy at high frequencies. This was so obviously not what happened. Real objects do not emit infinite energy, that the failure was given a name. It was called the ultraviolet catastrophe. This was not a minor discrepancy to be smoothed over. It was a fundamental breakdown of the wave picture applied to the emission of light. Into this impasse stepped Max Planck, a German physicist who was, by temperament, one of the most conservative scientists of his generation. Planck believed deeply in classical physics. He was not looking to overturn anything. He was looking for a mathematical trick that would make the numbers come out right. In 1900, after months of work, he found one. He proposed that the energy of a vibrating atom, the kind of atom that might sit in the wall of a blackbody and emit light, could not take on any value continuously, the way classical physics assumed. Instead, it could only exist in discrete steps. The atom could vibrate with 1 unit of energy, or 2 units, or 3, but nothing in between. And the size of that unit was not fixed. It was proportional to the frequency of the vibration. Higher frequency meant larger energy steps. This meant that at very high frequencies, the energy steps were so large that the thermal energy available in the system was rarely enough to climb even 1 step. High-frequency vibrations were, in effect, frozen out. Planck called these discrete packets of energy quanta, from the Latin word for how much. He derived a constant, a number that set the size of these energy steps, which we now call Planck's constant. It is an extraordinarily small number, but it is not zero, and that non-zero smallness is what separates the quantum world from the classical one. Planck himself was deeply uncomfortable with what he had done. He regarded the quantization as a mathematical convenience, a calculational device that happened to give the right answer, not a literal description of how nature worked. He spent years trying to find a way to recover continuous energy within a more conventional framework, and he never quite succeeded. The quantum had arrived, and it was not going to leave. 5 years later, in 1905, the same remarkable year in which Albert Einstein published his paper on special relativity, Einstein took Planck's quantum and went considerably further with it. The puzzle Einstein addressed was called the photoelectric effect, and it had been observed experimentally for some years without a satisfying explanation. When light is shone onto the surface of certain metals, electrons are knocked free from the surface. This in itself was not surprising. Light carries energy, and that energy can liberate electrons from the grip of a metal. What was surprising was the specific way it happened. If you increased the brightness of the light, sending more wave energy at the metal, you might expect more energetic electrons to be freed. But that is not what happened. Brighter light freed more electrons, but the energy of each individual electron remained the same. To increase the energy of the freed electrons, you had to increase the frequency of the light, and below a certain threshold frequency, no electrons were freed at all, regardless of how bright the light was. This made no sense under the wave theory. A wave is spread out, and a brighter wave carries more energy per unit area. If the electron simply absorbed wave energy until it had enough to escape, a brighter wave, even at low frequency, should eventually do the job. But it didn't. A dim beam of blue light would eject electrons when a brilliant flood of red light left the metal completely undisturbed. Einstein's explanation was elegant and, at the time, radical. He proposed that light does not actually travel as a continuous wave. It travels as discrete packets of energy, particles of light, each carrying an amount of energy proportional to the frequency of the light. A single packet of blue light carries more energy than a single packet of red light, because blue light has a higher frequency. When one of these packets strikes the metal, it interacts with a single electron, delivering its energy all at once. If that energy is above the threshold needed to free the electron from the metal's grip, the electron escapes. If it is below the threshold, as red light packets are for many metals, the electron cannot be freed no matter how many red packets arrive. Brightness means more packets, not more energetic ones. Einstein called these packets light quanta. The name photon, which is the word we use today, was coined by the American chemist Gilbert Lewis in 1926, and it stuck. This was an extraordinary claim. Maxwell's equations, the most precisely verified theory in 19th century physics, described light as a wave. Young's interference fringes were real and reproducible, and yet here was Einstein saying that light also travels as particles, not instead of waves, in addition to waves. The Nobel Committee recognized Einstein's photoelectric work in 1921, more than 15 years after he published it, partly because the implications were so strange that the community needed time to absorb them. By then, the experimental evidence was overwhelming. Light, it seemed, was genuinely both things: a wave when it propagated, a particle when it was absorbed. How that could be true, how something could be both a spread-out ripple and a localized pellet, was a question that the physics of 1905 was not yet equipped to answer. There is an experiment so simple in its design and so quietly astonishing in its result that Richard Feynman, one of the greatest physicists of the 20th century, once said it contains the only real mystery in quantum mechanics. Everything else, he suggested, is a variation on the same theme. The experiment is Young's double-slit setup, but performed in a way that Young could never have attempted, with a single photon at a time. Picture the apparatus, a source of light, dimmed so extraordinarily that it releases only one photon at a time. A single quantum of light, alone in the apparatus, with no other photon nearby. A barrier with two narrow slits, and behind the barrier, a detector screen sensitive enough to register the arrival of individual photons, marking each one as a tiny dot of light at the precise location where it lands. When the first photon arrives, it makes a dot, a single point on the screen, nothing more. It looks exactly like what you would expect from a particle, a tiny projectile that has come through one slit or the other and landed at a definite place on the screen. The second photon arrives, another dot, also random seeming, also a definite point. 100 photons, 1,000. Each one arriving as a single dot, each dot appearing to be placed at random. At this stage, if you looked at the screen, you might reasonably conclude that particles are flying through the slits and landing wherever their trajectories happen to take them. But something else is happening, slowly, in the accumulating pattern. After tens of thousands of photons have landed, the dots are no longer random. They have gathered into bands, alternating regions of high density and low density, bright and dark, spread across the screen in a regular pattern. And here is the part that simply will not yield to ordinary intuition. There was never more than one photon in the apparatus at any moment. There was no other photon for it to interfere with. Each photon, arriving alone, has somehow contributed to a pattern that requires two waves passing through two slits and meeting on the far side. The only possible conclusion, the one that physicists arrived at reluctantly over decades of experiment and argument, is that each individual photon passes through both slits simultaneously and interferes with itself on the far side of the barrier, not through one slit and not through the other, through both at the same time. How is this possible? The answer lies in a concept called superposition. Superposition is the idea that a quantum particle, before it is detected, before something forces it to have a definite position or a definite path, does not have a single definite state. It exists in a combination of all the possible states available to it, all at once. The photon approaching the double-slit barrier is not secretly traveling through one slit, and we just don't know which one. It genuinely has no definite path. It is in a superposition of the state, going through the left slit and the state going through the right slit, and both possibilities are equally real, simultaneously, until the moment of detection. This is not a metaphor or a shorthand for our ignorance. It is a literal description of the photon's condition, confirmed by every experiment ever designed to probe it. The photon is, in some deep and irreducible sense, in two places at once, spread across both paths, existing as a kind of distributed possibility, until it lands on the screen and becomes a single, definite dot. The mathematics that describes this is called the wave function, a mathematical object that encodes all the possible outcomes of a measurement and their relative probabilities. In the double-slit experiment, the wave function of the photon spreads through both slits, diffracts on the far side, and the two spreading portions overlap and interfere, just as water ripples do. Where the two portions of the wave function reinforce each other, the photon is likely to land. Where they cancel, it almost never does. The interference pattern is not a property of many photons. It is a property of the single photon's own wave function, written onto the screen one dot at a time. There is something almost meditative about watching this pattern build. Each individual event is random. You cannot predict where the next photon will land, but the pattern that emerges from many events is not random at all. It is precise, regular, governed by a deep mathematical law that the photon obeys even when it is entirely alone. The randomness of individual events and the regularity of the pattern coexist, neither one cancelling the other out. The image to hold, if you are still following. And it doesn't matter if you're not. Is this a single point of light arriving on a screen, carrying within it the ghost of a wave that passed through two places at once? The dot is particle-like, the pattern is wave-like, and both are completely, genuinely true. The natural question, once you have absorbed the strangeness of the single photon double-slit result, is this: can you catch the photon doing it? Can you set up some kind of detector at the slits? Some instrument that will tell you which slit the photon actually passed through, and confirm that it really does go through both? Physicists asked exactly this question, and they answered it. The answer is one of the most quietly unsettling things in all of science. When you place a detector at the slits, any detector of any kind, sensitive enough to record which slit the photon passed through, the interference pattern on the screen disappears. Completely. Tone. In their place, you see exactly what you would expect from particles. Two bright bands, one behind each slit, and nothing in between. The photons are now behaving like ordinary projectiles. They go through one slit or the other, land behind it, and accumulate into two simple piles. Turn the detector off, and the interference pattern returns. Turn it on, and it vanishes. The act of measuring which path the photon took has changed the outcome of the experiment. This is what physicists call the observer effect, though the word observer can be misleading. It has nothing to do with human consciousness, with awareness, with the act of looking in any psychological sense. What matters is physical interaction. Any detector that can record which slit the photon passed through must, by necessity, interact with the photon. It must absorb or scatter it slightly, or entangle itself with the photon's quantum state. And that interaction is enough. The moment the photon's path is physically recorded anywhere in the universe, even if no human ever reads the record, the interference pattern is gone. The reason lies in the superposition that made the pattern possible in the first place. For the photon to produce interference fringes, it must pass through both slits simultaneously. It must be in a superposition of both paths. But the moment a detector records which path was taken, the superposition is destroyed. The photon now has a definite path, a definite history, a definite answer to the question, which slit? And a particle with a definite path cannot interfere with itself because there is no second version of it to interfere with. The technical term for this destruction of superposition through interaction with a measuring device is decoherence, the process by which a quantum system loses its wave-like, spread-out character by becoming entangled with its environment. Any interaction that could in principle carry path information causes decoherence. There is a deeper principle at work here, one that the Danish physicist Niels Bohr spent much of his career articulating. He called it complementarity. The idea is that wave behavior and particle behavior are not two different things that light sometimes is. They are two complementary faces of a single underlying reality, and which face you see depends entirely on what you choose to measure. If you set up your experiment to reveal which path the photon took, to measure its particle-like location, you will see particle behavior. If you set up your experiment to reveal interference, to measure its wave-like spread, you will see wave behavior. But you cannot see both at the same time. The experimental choice forces the answer into one mode or the other. This is not a limitation of our instruments. It is not a problem that better technology will solve. It is a fundamental feature of the quantum world. The properties of a system are not fixed and waiting to be discovered. They are, in part, brought into being by the act of measurement itself. The gradual nature of this transition was demonstrated with particular beauty in an experiment published by physicists at MIT in 2025. Rather than a conventional double-slit apparatus, the researchers used individual atoms as the slits, a far more controlled and quantum-precise setup. They arranged things so that each photon scattered off at most one atom, and they could manipulate the quantum state of those atoms to control how much path information was available in principle. The result was a continuous and measurable fade, as the atoms were tuned to carry more and more information about which path the photon had taken. The interference fringes became less and less visible, smoothly and proportionally. Not a sudden switch from wave to particle, but a gradual dimming of the wave pattern as the particle information increased. This experiment confirmed something that had long been predicted but was difficult to demonstrate so cleanly. The wave and particle aspects of a photon are not simply on or off. They exist in a kind of balance, and gaining information about one comes at a precise and quantifiable cost to the other. The more definitely you know where the photon went, the less interference you will see. The less you know about its path, the more fully the wave pattern emerges. It is a strange and patient kind of physics. The universe does not resist being measured. It simply becomes, through the act of measurement, something different from what it was before. So far we have followed the photon through 2 centuries of argument and experiment. Particle, wave, both, neither, something that changes depending on how you look at it. But there is a deeper question underneath all of this, one that the experiments alone cannot quite answer. What kind of thing is a photon, at the most fundamental level that physics currently allows us to reach? The answer comes from a framework called quantum field theory, and it is worth approaching slowly. The old picture of physics, the picture that served well until the 20th century, imagined the universe as made of 2 kinds of things, particles and fields. Particles were the matter, electrons, protons, the small discrete objects that made up atoms. Fields were the influences that spread through space, the gravitational field, the electric field, the electric field, the electric field. Particles moved through fields, and fields acted on particles, and the 2 categories were distinct. Quantum field theory, developed through the middle decades of the 20th century, dissolved this distinction. In the quantum field picture, fields are the fundamental reality. They fill all of space, everywhere, always. And particles, what we call particles, are not separate objects moving through those fields. They are disturbances within the fields. Localized excitations, like a knot or a ripple in something that is otherwise smooth and still. An electron is an excitation in the electron field, an excitation in the electromagnetic field, the same field whose oscillations Maxwell described as light waves. The difference between the wave picture and the particle picture in this framework is not that one is right and one is wrong. A wave is a broad, spread-out disturbance in the field. A photon is the smallest possible disturbance, a single quantum of excitation, the minimum amount of electromagnetic field energy that can exist as a distinct unit. This is what a photon actually is, the smallest possible ripple in the electromagnetic field. It has some properties that follow from this nature in interesting ways. A photon is massless. It has no rest mass because it cannot be at rest. It always travels at the speed of light in a vacuum, because that is what disturbances in the electromagnetic field do. You cannot slow a photon down or hold it still. It exists only in motion. The energy a photon carries is entirely determined by its frequency, the rate at which the electromagnetic field oscillates within it. A photon of blue light oscillating at a higher frequency than a photon of red light carries more energy. This is the relationship that Planck first wrote down and Einstein confirmed with the photoelectric effect. The constant that links frequency to energy. Planck's constant is one of the most precisely measured numbers in all of physics, and it appears throughout quantum mechanics wherever energy and frequency are connected. Photons also carry a property called polarization. When the electromagnetic field oscillates within a photon, it oscillates in a particular direction, either up and down, or side to side, or in a rotating spiral. This direction of oscillation is the photon's polarization. It is a real physical property, not an abstraction, and it can be measured. Polarizing filters, the kind found in certain sunglasses, work by transmitting only photons whose polarization aligns with the filter's orientation and blocking the rest. Each individual photon either passes or doesn't, depending on the relationship between its polarization and the filter. And this single quantum decision is the basis of some of the most important applications in modern quantum technology. Now, there is one more property of the photon that is worth dwelling on, because it is perhaps the strangest of all. It concerns the photon's relationship with time. Einstein's theory of special relativity tells us that time passes differently for objects moving at different speeds. The faster you move through space, the more slowly time passes for you relative to someone standing still. This is not an illusion or a trick of perception. It is a real feature of the universe, confirmed by measurements of subatomic particles and even by the clocks carried on GPS satellites, which must be corrected for relativistic time effects to keep the navigation system accurate. Now carry that logic to its limit. A photon travels at the speed of light. At that speed, the relativistic equations predict that time slows to a complete stop. From the photon's own perspective, if such a thing could meaningfully exist, which is philosophically uncertain, no time passes at all between the moment of its creation and the moment of its absorption. A photon emitted by a star, 8 light minutes from Earth, and absorbed by a human retina has, from its own frame of reference, experienced no duration whatsoever. The emission and the absorption are, for the photon, the same instant. This means that in a very deep sense, the photon does not travel. It simply connects 2 points in space-time, its origin and its destination, with no experience of the journey in between. The 8 minutes that pass for us, the vast distance crossed, the whole span of the photon's flight across space, all of that exists only from the perspective of the things that are not moving at the speed of light. For the photon itself, there is only the moment of its making and the moment of its ending, with nothing in between. It is an image that asks to be held very gently, without pressing too hard on it, a messenger that experiences no journey, a connection without a crossing. There is a phenomenon in quantum physics that Einstein found so troubling that he spent years trying to prove it could not be real. He did not succeed. The phenomenon is called entanglement, and it is perhaps the most counterintuitive thing that careful experiment has ever revealed about the universe. To understand what entanglement means for photons, it helps to begin with polarization, which we encountered in the previous chapter. A photon's polarization, the direction in which its electromagnetic field oscillates, is a quantum property. Like all quantum properties, it does not necessarily have a definite value before it is measured. A photon can be in a superposition of polarization states, genuinely undecided between horizontal and vertical, until a measurement forces it to choose. Now imagine a process in which 2 photons are created simultaneously in the same physical event. This can happen through a process called parametric down conversion, a name that sounds technical but describes something with a certain elegance. A single high-energy photon enters a specially prepared crystal, and within that crystal it is converted into 2 lower-energy photons. Because the 2 daughter photons are produced together from the same parent, the laws of physics require that certain properties of the pair are correlated. In particular, their polarizations are linked in a specific way. For instance, if one is measured to be vertically polarized, the other will always be found to be horizontally polarized, or the 2 will always match, depending on how the crystal is set up. So far, this might not sound particularly strange. You might imagine that the 2 photons simply share some pre-existing agreement about their polarizations, the way 2 gloves from the same pair are already matched before you open the box, one left, one right, decided in advance. But quantum mechanics says something different, and experiments confirm it. The polarizations are not decided in advance. Before either photon is measured, both are in a superposition, genuinely undetermined. The decision is made only at the moment of measurement. The decision is made only at the moment of measurement. And yet, the moment you measure one photon and it settles on a particular polarization, the other photon, no matter how far away it is, instantly settles on the correlated polarization. Not because a signal has been sent between them, not because they communicated, but because their quantum states are not two separate states at all. They are one shared state, describing both photons together, and measuring one part of that shared state collapses the whole thing simultaneously. This is entanglement. Two particles sharing a single quantum state, such that what happens to one is instantly reflected in the other, regardless of the distance between them. Einstein was deeply uncomfortable with this. In 1935, together with colleagues Boris Podolsky and Nathan Rosen, he wrote a paper arguing that if quantum mechanics predicted this kind of instant correlation across arbitrary distances, then quantum mechanics must be incomplete. There must be hidden variables, pre-existing properties that determine the outcomes in advance, like the gloves in the outcomes in advance, like the gloves in the box. He called the alternative spooky action at a distance, and he did not mean it as a compliment. For 30 years, the debate remained largely philosophical because no experiment could definitively settle it. Then, in the 1960s, a physicist named John Bell worked out a precise mathematical test that could distinguish between the quantum prediction and any hidden variable theory. If the correlations between entangled particles were stronger than any pre-existing agreement could produce, that would be evidence that the correlations were genuinely quantum, that there were no hidden variables, and that spooky action at a distance was real. Beginning in the 1970s and accelerating through the 1980s, experiments, most famously by the French physicist Alain Aspect and his colleagues, tested Bell's inequality with entangled photons. The results were unambiguous. The correlations were stronger than any hidden variable theory could explain. Entanglement is real. There are no hidden pre-existing agreements. The photons genuinely do not have definite polarizations before they are measured, and measuring one instantly fixes the other. Einstein was wrong about this one. The universe is, in this particular way, spooky. The practical consequences of entanglement are still being discovered. In quantum cryptography, entangled photon pairs can be used to distribute encryption keys between two parties in a way that is, in principle, impossible to intercept secretly. Any eavesdropper who tries to measure the photons in transit must interact with them, and that interaction disturbs the entanglement in a way that the legitimate parties can detect. The eavesdropper cannot read the message without leaving a trace. The security comes not from the complexity of a mathematical problem, but from the laws of physics themselves. More recently, entangled photons have found a role in a different kind of application: imaging. The EU-funded FASTGhost project, which published significant results in late 2024, is using entangled photon pairs to image biological tissue in the mid-infrared range, a part of the spectrum where many molecules have distinctive absorption patterns, like fingerprints, that can identify them without any chemical labeling. The technique uses the quantum correlations between the photon pairs to reconstruct images of samples that the photons never directly illuminated, achieving sensitivity and resolution that classical light sources cannot match. The goal is to identify molecular structures in living tissue, proteins, lipids, the chemical signatures of disease, without damaging what is being observed. There is something quietly beautiful about this. The strange quantum connection that Einstein called spooky has become, in the hands of experimenters, a tool for seeing what ordinary light cannot see. The eeriness of entanglement put to gentle use. And now the journey turns inward. We have followed light from the ancient argument about its nature, through the mathematics of waves and the puzzle of quanta, through the mystery of a single photon passing through two places at once, through the strange physics of observation and entanglement. All of that has been, in a sense, a long and patient approach to this final question. What happens when a photon reaches you? Not you as a detector in a physics laboratory. You, here in the dark, with your eyes closed and your breathing slow, and the day already beginning to feel distant behind you. The story of light and the human body begins at the back of the eye in a thin layer of cells called the retina. Most people know that the retina contains rods and cones, the photoreceptors that give us vision in dim light and in color, respectively. But there is a third type of cell in the retina that was only discovered in the late 1990s and early 2000s, and its role has nothing to do with forming images. These cells are called intrinsically photosensitive retinal ganglion cells. The name is long, and it doesn't matter if it doesn't stay with you. What matters is what they do. Unlike rods and cones, which send visual information to the image-forming parts of the brain, these specialized cells send their signals along a dedicated pathway to a small, ancient cluster of neurons deep in the brain called the suprachiasmatic nucleus, from the Greek words for above and crossing, because it sits just above the place where the optic nerves cross each other. This nucleus, no larger than a grain of rice, is the body's master clock. It generates and coordinates the roughly 24-hour rhythm that governs almost every biological process in the human body. These light-sensitive ganglion cells contain a photopigment, a light-absorbing molecule called melanopsin. And melanopsin is not equally sensitive to all wavelengths of light. It has a peak sensitivity at around 480 nanometers, which places it squarely in the blue portion of the visible spectrum. Not the deepest blue, not violet, but a soft sky blue, not violet, but a soft sky blue wavelength. The kind of wavelength that is abundant in daylight, particularly in the open sky on a clear morning. When a photon of the right frequency, around 480 nanometers, reaches one of these cells, it is absorbed by a melanopsin molecule. This absorption is a quantum event. A single photon, with its particular energy, is taken up by a single molecule, and the energy is used to change the molecule's shape. That shape change triggers a cascade of biochemical reactions, a process called phototransduction, meaning the conversion of light into a biological signal. Phototransduction is the mechanism by which all photoreceptors in the eye work, but in these specialized cells it has a different destination. The signal travels not to the visual cortex, but along a pathway called the retinohypothalamic tract, directly to the suprachiasmatic nucleus. The nucleus receives the signal and registers. There is light. It is daytime or something close to it, and it adjusts the body's rhythms accordingly. One of the most important things the suprachiasmatic nucleus controls is the release of melatonin from a small gland in the center of the brain called the pineal gland. Melatonin is a hormone that the pineal gland releases into the bloodstream, and its concentration in the body is one of the primary signals that tells every cell what time it is. In daylight or in the presence of blue light at night, the suprachiasmatic nucleus suppresses melatonin production. The body remains alert, its rhythms tuned to wakefulness. As darkness falls and the blue light signal fades, the suppression lifts. Melatonin begins to rise, slowly and steadily, reaching its peak in the deep hours of the night. And it is this quiet, gradual rise of melatonin in the blood that draws the body towards sleep. Not a switch, not a sudden drop into unconsciousness, a slow, patient dimming. The body following the ancient rhythm that light has set for it, responding to the absence of photons the way a flower responds to the absence of sun. The sensitivity of this system is remarkable. The light-sensitive ganglion cells are far less numerous than rods or cones, and their individual probability of capturing any given photon is much lower. But they are designed for sustained, slow signaling rather than rapid image formation. And they respond most strongly to the blue wavelengths that are most characteristic of natural daylight, which is why artificial blue light from screens and LED lighting can be so effective at delaying the melatonin rise. It mimics, at a biological level, the signal of an afternoon sky, even when the hour is late. Now hold the whole journey in mind, very gently. A photon is born in the sun, produced by the nuclear fusion deep in the solar core, where hydrogen nuclei join together and release energy, some of which eventually makes its way outward through the layers of the sun and escapes into space as light. That photon travels for approximately 8 minutes across roughly 150 million kilometers of empty space, its electric and magnetic fields oscillating at hundreds of trillions of cycles per second, carrying a tiny, precise quantum of energy. It enters the atmosphere, it scatters among molecules and dust, it passes through glass or a gap in a curtain or the open air of an evening window. It travels the last few centimeters to your eye. At the retina, it is absorbed. One photon, one molecule of melanopsin, one quantum event too small to feel or see or know. And yet that event, that single, instantaneous, entirely silent interaction, is registered by the body's clock. The signal travels to the suprachiasmatic nucleus. The nucleus notes the hour. The melatonin curve adjusts by a fraction. Over the course of a day, millions of these events accumulate. The clock is set and reset continuously by the light that falls on the eye. And as evening comes and the photons of blue light grow scarce, the clock releases its hold on wakefulness, the melatonin rises, and the body begins to do what it has done every night for as long as there have been creatures with eyes. It turns towards sleep. There is something worth holding in this, even lightly, even half asleep. The quantum strangeness we have spent this hour exploring, the wave-particle duality, the superposition, the measurement that changes what is measured. All of it is not remote or abstract. It is happening right now in the cells at the back of your eyes. Every photon that has reached you today has been a quantum event. Every signal your body's clock has received has begun with the absorption of a single, indivisible packet of electromagnetic energy, governed by the same laws that baffled Newton and Planck and Einstein. The universe's deepest strangeness is not somewhere out there in a laboratory or a distant galaxy. It is in the quiet biochemistry of a body preparing for sleep, in the slow rise of a hormone in the blood, in the ancient rhythm that has been counting days since long before there were words for light, or waves, or particles, or any of the things we have spoken of tonight. The day is already far behind you. The clock inside you has been reading the light all day, and now it is reading the dark, and it knows what the dark means. Drift now, if you're ready. Sleep well.